We present dual-space NeRF, learning animatable avatars and scene lighting in separate spaces, a method that learns to reconstruct a person from synchronized sports view video frames and animates the subject with normal poses. Neural binds features onto the vertices of simple and diffuse them into the space before volumetric rendering. This method feeds spatial location X into the color model to help with fitting, but causes degradations on normal poses. Animatable NeRF learns a human body in a canonical space, but lacks exploration in lighting inconsistency. Besides, its neural network for blending weights requires fine-tuning for normal poses. Given that the environmental lighting is almost static for indoor scenes, we propose dual-space NeRF, which models the scene lighting in the world space and the human body in the canonical space. This is the key to the lighting correctness of our method and unseen poses. In the canonical space, we feed a point position, pose features, and a latent embedding into a body MLP to predict density and texture. In the world space, we feed a point position, a viewing direction, and a surface normal into a lighting MLP to predict a lightness coefficient, which adjusts the brightness of the texture to obtain the color. To bridge the spaces, we propose the Barycentric mapping based on a local description, which can directly generalize to normal poses. Concretely, we map a point position from the world space to the canonical space, and transform a surface normal from the canonical space to the world space, both with the Barycentric mapping. We compare of our method with two state-of-the-art methods. The lighting conditions in our results are closer to the ground truths, and the details are easier to recognize. In quantitative evaluations, our method shows clear advantages on all three metrics. We also animate a subject from each dataset with a pose sequence from the other dataset. Our results show higher visual quality with fewer artifacts. Furthermore, we tested the methods with challenging pose sequences from the MS database. Neural body can hardly generalize to extreme poses. Animatable NeRF lacks details such as wrinkles and lighting, while our method gives stable and sharp results. To validate the virtue of the Barycentric mapping, we replace it with the inverse LBS algorithm. Both the quantitative and the qualitative comparisons shows the clear superiority of the Barycentric mapping, especially on normal poses. Inverse LBS produces artifacts near movement-frequent places like armpits and feet. To test the usefulness of the Lighting MLP, we disable it when training and rendering. Then our model degrades to a vanilla NeRF and shows significant decline in all metrics. We also try an alternative design of the Lighting MLP that takes in the body texture and outputs the color, but observe color overfitting. We visualize the effects of the Lighting MLP by rotating the query points along a certain axis. However, if the subject walks out of the moving boundary of the training frames, the rendering results will be dim because those locations are undefined for the Lighting MLP. Thank you.